the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
The Stevens Institute of Technology is proud to present the Hugo New Corporation Sustainability Seminar Series, brought to you by Brown & Codwell, Geocetic Consultants, H2M Architect and Engineers, BEM Systems, and Catalyst Group.
So Harold, did you want to start with just this slide and then I'll jump in?
Absolutely. So as our professor mentioned, we'll be covering one of New Jersey's Transit's resilience program projects, the Raritan River Bridge replacement and its associated compensatory mitigation. Specifically, we refer to it as the New Jersey Transit Coastal Maritime Shoreline Restoration, a Sustainable Design.
Thanks, Harold. So again, I just want to say thank you for letting me speak tonight. Very happy to be here. Certainly have worked with the professor before, and I'm very happy to be part of tonight's presentation. So just to explain exactly what we're going to see tonight, I know the slide is probably just loading here, but tonight we want to spend a little bit of time talking about what Harold had mentioned, a sustainable shoreline restoration project associated with one of New Jersey's capital projects, which is the reconstruction of the Raritan River Bridge. So the genesis of what Harold will talk about a little later in the slide program is based on a project to actually replace a rail bridge. And it's got some interesting history, and I'll kind of go through that as I speak. But I wanted to make sure that you understood what we're going to cover during the seminar. So I want to spend a little bit of time, not too long, but a little bit talking about New Jersey Transit's resilience program and what that means to New Jersey Transit. Want to explain what the project at hand is that led to our shoreline restoration efforts. Want to understand a little more about coastal maritime mitigation design, and Harold will speak in more detail about that. Want to talk a little bit about how the project worked well into a local coastal habitat and how it supported that habitat and will continue to support that habitat after the construction's finished. And then, of course, if there are questions, we're happy to sort of stick around and host those if that's something that's pursued. So first and foremost, New Jersey Transit. I think, assuming that the audience is mostly local, I'm assuming that most people know what New Jersey Transit is. So New Jersey Transit is actually the nation's largest statewide transit agency. And that's a curious distinction, right? So when you think of transit agencies, mostly you associate them with cities, the city of New York, city of Buffalo, the city of Los Angeles. New Jersey Transit actually covers the entire state of New Jersey. So of the 8,700 square miles that make up the Garden State, we have about a 5,000 square mile service territory, which is a pretty significant, in fact, it's the largest among any transit agency in the country. We serve commuter markets in the Philadelphia and New York City market, and then of course, all points in between in New Jersey. On the rail side, we have 11 different rail lines. And on the bus side, we have about 2,400 buses in daily service. And again, I have to preface my comments by saying this was all true prior to COVID. We are still running full service during COVID, and we're very enthusiastic to get our rider base back as COVID begins to wane. We encourage all of you to ride New Jersey Transit as much as possible. Our system is clean and safe. Come on back to Jersey Transit. So there's my shameless pitch for New Jersey Transit there. A couple things about the resilience program. So New Jersey Transit was the beneficiary back in 2014 of some resilience grants. These were federal grants that we were given, and they were designed to provide New Jersey Transit with funding after Superstorm Sandy. So again, Sandy struck in 2012. Here it is 2021. So you may wonder, well, what it's taken so long? Why does it take so long to spend money and to build and do things? Well, there's a lot of answers to that. And I think we'll probably go through some of that as we discuss the Raritan River Draw project. But first and foremost, there are 5 or 6 projects that fit under our resiliency suite. One of which is the reconstruction of the bridge we're about to speak about. So the particular bridge I want to spend some time on that Harold will talk about in terms of coastal resiliency is what we call the Raritan River Draw, D-R-A-W, draw. And the bridge has a kind of an interesting history. The original bridge was built in the late 1800s and served the area until the early 1900s. It was rebuilt around that time to its current configuration. And here it is in 2021. We're actually endeavoring to rebuild it again. The bridge did suffer some damage during Hurricane or Superstorm Sandy. The damage was repaired, but the bridge structure itself was definitely in need of upgrading, updating. So just to give you an idea of where the bridge is, you can see on the slide on screen there that the northern terminus of the bridge is Perth Amboy, the southern is South Amboy, and it crosses the Raritan River, the estuary there, at probably one of the strangely enough, it's one of the narrower points as you begin to approach the Atlantic Ocean. So again, the original railroad builders, the New York and Long Branch Railroad, which later on became the Pennsylvania Railroad, sited the bridge at a location where they thought a crossing made sense. It does make sense, continues to make sense. And the bridge is located not far away from the Driscoll Bridge, which carries the Garden State Parkway across the same area, as well as, I believe, the Route 27 bridge. So just to locate you in terms of where we are in the state of New Jersey here. Harold, next slide. So again, what is the bridge's purpose? On screen there, you can see a picture of the existing bridge. It's a low span bridge. You'll notice the bridge does have poles associated with it. Those poles support a catenary structure, so the bridge supports an electrified rail operation. Catenary really are the wires that are strung above railroad tracks that form the basis of electrical traction for locomotives that can take advantage of that traction. So New Jersey Transit does have electrified rail service in the area. The bridge is a critical link between really North and Central New Jersey. The bridge is part of our North Jersey coastline. Again, it was built in the middle to late 1800s, originally by the New York and Long Branch Railroad. We follow basically the same alignment. The bridge itself carries not only New Jersey Transit, but of interesting note to the project, the bridge also does carry some freight traffic in the what they call the Conrail shared assets territory. So it forms an important link for both freight traffic as well as commuter traffic across the Raritan River. So during the course of in the time shortly thereafter, Superstorm Sandy in 2012, the bridge did receive some damage. The damage was repaired, but as I mentioned earlier, there were some damages to the structure that really needed to be repaired in a significant way by a full bridge replacement. New Jersey Transit did submit the project to the Federal Transit Administration, the FTA, which is our grant administrator, and it won a resiliency grant for replacement. It's a significant high dollar value project. About $650 million to replace the bridge. But then I'm sure, as you can imagine, bridges are expensive to replace. There's a great deal of timing and coordination that has to go into how the bridges get replaced. Now, the bridge itself was closed for a period of time after Superstorm Sandy. Right now, due to its condition, trains operate at a slower speed. And there are some weight restrictions on the bridge. And again, the weight restrictions don't apply too much to New Jersey Transit services, but as you can imagine, they apply more to the freight services. Again, the goal in replacing the bridge is to remove those restrictions, speed for passenger and weight for freight, and to make sure the bridge is invulnerable to future storm events. We do currently maintain the bridge. It's actually a relatively expensive bridge to maintain. It's a relatively long bridge. And those maintenance activities, unfortunately, they're not going to address the long-term needs to strengthen the bridge itself. That'll only be met by the replacement of the bridge. Harold, next slide, please. So when we take a look at a project, we need to sort of state a purpose and objective, or a purpose and need. So obviously the replacement of the Raritan River Bridge is to bring about the purpose of a more resilient structure that services the needs of transportation in this part of New Jersey, both public transportation and, of course, private freight transportation. We want to make sure that the new bridge design will make it more resistant to storm events and to ocean surges associated with storm events. We want to make sure that we raise the tracks and some of the electrical and mechanical systems on the bridge to a better design flood elevation to make sure that it's less vulnerable to wind and wave action. We want to make sure that any components that we install can better withstand saltwater, ocean surge. Again, anything to do with water. Keep in mind, I had mentioned that the bridge was, in fact, able to service electric traction. So a good component of the bridge is some of the components that feed that electrical traction system. So the goal here was to make sure that that system would not be vulnerable to additional wind and wave action. We wanted to make sure that its structural capacity is able to comply with current codes, and I'll speak more about that later. But as you might imagine, bridges that were built 100 years ago, you know, they're probably not, I shouldn't say adequate, but they're not as adequate as they could be for increasing size and load. And that's especially true on the freight side. In fact, on the freight railroading side, we've seen a significant increase in car capacity in terms of weight. So that seems to keep on going up. Every time you increase the weight of rolling stock, you've got to take a look at your road bed, your track bed, and of course any structures across it, such as a bridge, to make sure that it's able to maintain its structural stability and integrity when compared with the loads that are crossing it. We wanted to make sure also that replacing the bridge would not sacrifice service on the New Jersey coastline, and that any changes we made to service would minimize its effect on people. So again, all lofty goals and objectives, not easy to reach, but all necessary for us to be able to accept federal dollars to make this improvement. Harold, next slide, please. So more specifically, some of the improvements that will be made as we replace the bridge, and we'll go over what kind of bridge we're going to replace in a second. But it needs to be designed to meet our design flood criteria. And I mentioned that was basically 2.5 feet above design flood elevation. And Harold will talk a little more about that later on, most likely. But New Jersey Transit does have design criteria. Right now, our criteria is 2.5 feet above what we call base flood elevation. As we look at things like sea level rise or the increasing frequency or intensity of storms, we're going to need to revisit that number. In fact, right now, the New Jersey DEP and the governor's office is really developing a pretty sound resiliency plan, and then thereafter regulations to support it that will take a careful look at flood elevation in light of threats such as sea level rise and, of course, the frequency and intensity of storms. I mentioned earlier that we want to be able to accommodate heavier freight trains, right? So the current heavy standard now of freight cars is 286,000 pounds per car. So that's a significant weight. Freight railroads are looking to petition the Federal Railroad Administration to raise that even higher, up to 315,000 pounds per rail car. So that's pretty significant. So when you think about the weight of things, just so you have a way of referencing it, a typical New Jersey Transit multi-level coach weighs about 70 tons, about 70 tons. So here you're talking about a freight car that weighs in excess of 150 tons, more than double that. So again, freight cars are heavy. As they trundle along, they create a lot of stresses on both rail, track bed, track structure, and of course, especially bridge structures. We also wanted to design the bridge such that we're going to be able to afford to maintain it, which is an important consideration going forward. And I mentioned some of those things that we wanted to do to support that, which is to make sure that critical components are raised out of harm's way regarding wind and wave action. The other important thing about the bridge that's of note is this particular area, whereas it doesn't have a lot of commercial marine traffic, it used to in the past, doesn't so much have a lot now. It does have a lot of recreational marine traffic. And we wanted to make sure that one constant conflict, of course, when you have a bridge over water and there is marine traffic, is who has the right of way, right? So do boats, when they sound their horn, is that the signal to raise the bridge, or is it based on the rail schedule? It really depends on a lot of different factors. But at the end of the day, what you really want to try to do when you have a crossing of a bridge is to eliminate or minimize how many times the bridge has to raise. That allows for better marine traffic navigation, as well as fewer delays on the rail side. We wanted to make sure that we were able to widen the channel below the bridge itself as much as possible. That also is a safety enhancement for marine traffic. And we wanted to make sure that marine traffic itself, again, the recreational traffic, which is important, is maintained in the area. Harold, next slide, please. So a couple of alternatives that were considered as we looked on bridge design are shown on this slide here. So again, when we've looked at alternatives, of course, there's a no action alternative, and these terms kind of come from the National Environmental Policy Act process, what we call the NEPA process, which is an environmental planning process. So when you look at a major project and you look at it from an environmental planning perspective, the first thing you take a look at is, well, what if I took no action? What would be the result? And the result would be that the continuing operation of the bridge would deteriorate its condition to a point where it would be no longer usable for rail traffic. So obviously that's the no action alternative is not a real good alternative when you take a look. We also took a look at, could we rehabilitate the existing structure? Would that make sense? Could we rehabilitate it to a point at which it would be able to support 315,000 pound freight cars and 60-mile-per-hour rail traffic? And when we took a look at that alternative, we understood that the amount of money it would take to rehab the existing structure was actually more than it now takes to replace the structure. And then finally, we looked at replacement alternatives, and we have on screen there a couple of different pictures of the, I guess I'm going to call it the latest technology in movable rail bridges. Believe it or not, this technology hasn't changed in a long time. But let me start on the bottom left. So you see what's called a Vascular Bridge. Not a very common bridge type anymore. All of our bridge designers had experience in building these. None of them have been built recently. These are the bridges with those very, very large concrete counterweights that helps the bridge roll to an open position. Notice there needs to be sort of a central landing platform, the Vascular design. Above that is a swing bridge, and the swing bridge actually is what's there now. So the existing Raritan River drawbridge is a swing bridge. It's called a center pivot swing bridge. And if you look closely at that slide, you can see in the middle there actually is a sort of a casement, a round sort of a concrete and steel pedestal. The bridge actually rotates on that pedestal. The challenge, and again, this was the center pivot swing bridge was a pretty common type bridge built in the early part of the 20th century, and that kind of explains why this bridge was built to that engineering standard. These days, it's less common. One of the drawbacks to the center pivot bridge is a couple things. One is when the span pivots back to its rail position to maintain a straight axis with the rail, it's a little bit tricky to get the rails to line up and to mechanically integrate again. So there are sometimes problems with that. Great example is the Portal North Bridge, which is another well-known bridge in the area. That's a center pivot bridge. It carries Amtrak and New Jersey Transit across the Hackensack River. Once in a while, you'll hear on the radio in the morning that bridge was open for marine traffic, but it's having a difficult time resetting its position for rail traffic, and that can cause significant delays. The other problem with the center pivot bridge is the same for a Vascular Bridge. If you look at the channel below the bridge, it's bisected by that island in the middle. And that island in the middle takes up navigation space. It also creates a navigation hazard, and it limits the width of vessels that can pass under the bridge. So to replace the Raritan River Draw, New Jersey Transit and its designers settled on the bridge type that's seen to the right there. So that's a center span lift bridge. So those two towers on either side of that truss work in the middle actually lifts that bridge straight up. Obvious advantages there is the marine channel in the middle is now much wider. The disadvantage here, of course, is now you have a vertical height restriction. So when we work closely with the Coast Guard to permit this type of bridge, they were very interested in the height restriction because that does limit marine traffic. So we had to make sure that this bridge's height restriction was no less than other bridges upstream of this bridge. So that was an important consideration. So actually, when this bridge is built, it'll have two of the highest towers of any lift bridge in North America. So of note there. Harold, next slide, please. So just a quick thing before I turn over to Harold. We talk here about the design flood elevation. I mentioned for New Jersey Transit, we had to work closely with our grant agency, FTA, to ensure that the design flood elevation that we chose to implement with the bridge was consistent with resiliency standards at the time. So we relied on FEMA mapping, flood mapping. We took a look at the New Jersey Uniform Construction Code, which we're responsible to follow for structures that involve the public. We also took a look at the time at the best available science data. We took at the 500-year floodplain elevation. We took a look at climate science and where things were going. And we came up with our design flood elevation based on those inputs. So next slide, please. Kind of gives an idea, and again, Harold will kind of take over past this slide, but for the most part, we chose a profile and an elevation that is consistent with our base flood elevation plus 2.5 feet for the design flood elevation. We wanted to make sure, and this was kind of an important thing with this bridge, I mentioned it carries freight traffic. And if you can imagine, a freight train with several cars of 315,000 pounds, they don't climb hills too easily. So the approach to the bridge really needed to be carefully weighed out. The approach to the bridge will be a little higher than the existing bridge, and that's consistent with our base flood elevation design, or I'm sorry, our design flood elevation. It also helps us to keep critical components out of the water, but again, the design couldn't be too high. Some people have asked, well, why not build a bridge that doesn't have a movable span? Why not build a bridge as high as a highway bridge? I think the obvious answer there is that the approaches for the bridge would have to be so far inland to avoid a grade that it would make the bridge, otherwise it would make the bridge unusable for rail traffic. And to put the approaches that far inland would involve a great deal of a property taking and whatnot. It would be a hugely expensive concept. So this bridge is higher than the existing Raritan River Draw. It'll serve that purpose for resiliency. It'll meet our design flood elevation, but it'll still allow trains to maintain a 60-mile-an-hour passenger limit and allow freight trains to climb up and over and down the bridge safely. At this point, I'm going to ask Harold to jump in and take us through the balance of some slides, more specifically about some of the mitigations that were required by the construction project and how Harold and his team work with New Jersey Transit to achieve those. Harold?
Can you guys hear me?
We can.
Okay. Yeah, so just to add to this slide, John, I would just say to the group, basically there were specific segments of the alignment that could not be raised at the DFE. So those specific areas were, their critical electrical components were raised or hardened specifically as needed. So we'll move on here. All right, so in terms of you heard a little bit about the bridge improvements itself, and consistently with the improvements, there's obviously a permit effort to authorize that with DEP and the Corps. We went through that formal process. A component of that permitting effort was obviously to meet mitigation compliance for any impacts to coastal wetlands, subtidal, intertidal shallows. Overall, the impact for the project was about 0.437 acres. we selected a site that John had shown initially in the overall aerial, which is literally on the northwest section of the project itself. This is the existing aerial of what that mitigation site looks like. Currently, there's areas that need some remediation. There's a lot of rubble and debris, which was kind of the historic old-fashioned way of hardening shorelines. Basically, whenever there were roadway improvements and debris from those roadway improvements or construction debris, sometimes that was dropped and hardened along shorelines to really protect them from the dynamic impact of tidal waters. So this is the site we have selected, the specific site. The mitigation that's being proposed is an increase of wetland resources in comparison to what was impacted. The increase is about 0.265 acres. The image I have here on the bottom are basically our before and after when you consider kind of an old minimalistic mitigation method where we would look at the site we selected and we would say, all right, let's clean it up. Let's propose the area be graded to a certain elevation based on tidal fluctuations, implement natural vegetation, diversify the habitat a bit, and obviously provide a public component, considering there's a waterfront area. So this was kind of a before and after of what that would look like if you worked with the existing elevations at the site and didn't take into consideration other factors, whether it be truly diversifying it, increasing your edges, providing habitat, whether it be for avian, terrestrial, or aquatic species, and definitely not considering future sea level rise components and how that could impact your site. So we kind of went out of the box and looked at other mitigation options and measures that we could implement. So this could be a long-standing mitigation project that also provided kind of a first line of defense natural barrier for other inland improvements and inland areas. The focus was basically a beach dune restoration. The reason being was this is one of the smallest habitats that exist within this watershed. And really, there's a sincere need for those areas to be conserved and restored, considering the Raritan watershed is a major corridor for certain aquatic species, a nursery area, obviously a part of the migration corridor for raptors, for neotropical birds, and things of that nature. We wanted to obviously achieve restoring the lost historic wetland functions and values that were basically required from the proposed project, and obviously remediate the site, provide ecological functions, and improve habitat for wildlife, prevent flood damage, and address sea level rise resilience for the project. So what does the mitigation provide in general? The way it was designed and reconsidered, it provides floodwater storage. It provides in general TSS removal, filtration from your landward side, and the quality of water that's being discharged onto your bay or tidal waters. And it also provides filtration on the aquatic side itself with some of the measures we put in, specifically with the oyster reefs or whelk reefs that are going to be implemented. A diversity of habitat that's going to support fish, nursery and spawning functions, provide shelter, baseline benthic resources with the living shoreline that's been proposed, we're installing reef balls, whelk reefs, and intertidal vegetated areas. As I mentioned before, this will provide some benefit for neotropical species. On the landward side, because it is a beach dune habitat and coastal habitat that we're restoring here, we decided to integrate some man-made structures that would benefit local endemic species, specifically tree swallows and ospreys as well. So I will show you later on in a slide where that specifically is going to be. One key factor or species that this type of mitigation, aside from its resilient component, is diversity in habitat serves to address specifically state threatened and federally endangered species like red knot, which is pictured here, which obviously migrates from South America all the way to the northern Canadian Arctic regions. And there's thousands and thousands of these specific species that use New Jersey as an intermediate feeding ground. They predominantly feed on crab eggs and other benthics that are found in the resources that we intend to integrate. So thinking of the aerial that I showed you previously, this is kind of topographically how we would modify the site. Obviously, we're looking not just at a vertical improvement, but also an improvement of habitat and edges and ecotones from the subtidal side of the property, which is basically starting with your reef balls and how that functions for aquatic species as a source of shelter, a source of breeding and feeding. And then the kind of herringbone placed oyster reefs or whelk reefs. The reason they are placed in this specific alignment is they serve a dual function of not just providing habitat and resources for foraging, but they also work as a natural defense, and also as the tide kind of goes through its ebb and flow and recedes, there's always a deposition of sediment north of those structures, which actually start to, in time, replenish the beach behind it. So they serve as a natural mechanism to restore natural elevations on the beach side as well. Rather than create an engineered hardened structure like a retaining wall as a defense mechanism against tidal interactions and surge and sea level rise, we decided to put natural boulders and interplant those areas as they proceeded up into your primary dune and your secondary dune. You can see also on this plan, there is a public walkway component and obviously a staging area for New Jersey Transit in the future to use for maintenance purposes of the bridge. This public access component will tie into a future amphitheater that the city of Perf-Amboy is pursuing in the future. So this would be a great opportunity to invite the public to basically the waterfront area and really learn what resources exist and why they are not just important, but critical for protection of our inland resources. So one thing to consider with regards to this mitigation effort was, aside from just doing a straight mitigation, how could we do something that could withstand the test of time and obviously an increase of sea level rise due through climate change and other factors. The rate of impact on existing wetlands, settling of historic wetlands, et cetera, is a real factor. So we looked at the sea level rise as it relates to New Jersey's rising seas and changing coastal storms. The STAP report, which really provided a localized projection in terms of sea level rise for New Jersey. You know, other resources like NOAA provide more of a generic resource and forum, which really couldn't be specifically applied to our circumstance here. So we looked at the projections for the mitigation project. They used the most conservative approach, which corresponded to the 95th percentile projection of sea level rise under the high emission scenario. And if anyone's interested, this is all public information. You know, you could obviously access that. There's a whole explanation of how the STAP report was developed and how sea level rise was projected for New Jersey specifically. The thought of is New Jersey is at higher risk than other states from tectonic rebound. And that's why this specific report was a great resource for us. So the purposes of the analysis was about evaluated against the 95th percentile as mentioned. The high scenario in the staff report provided an elevation of 8.8. That's circled here on this specific table in the year 2100. So the mitigation site was designed to withstand dynamic interchange at that elevation up to the year 2100. So when you applied design flood elevation for the year 2100 and the projected base flood elevation of 12.8 feet, plus a 1 foot factor for safety and the 8.8 foot sea level rise consideration, the 22.6 feet overall was the projection. We looked at that against our mitigation site to see how it would withstand that, to ensure that we were providing a resilient design that just served dual functions of withstanding sea level rise in the future, obviously diversifying the habitat in this limited space we had, and providing a service for various endemic species, whether they were aquatic, terrestrial, or avian. This cross section here kind of relays, and it may be a little hard to see, but I'll explain a little bit of what we're showing here. So we're at the tidal interchange area, where basically the shoreline reef balls and the reef oyster reefs would be put in place. That would be the first line of defense and habitat improvement. Then there would be an intertidal vegetated area just above that. That also serves as a nursery, as a foraging area for various species. And then you would have an increase of a kind of boulder shoreline, more of a natural hardened area interplanted with vegetation from beach dune vegetation, and we diversified that with fruit-bearing species, seasonal fruit-bearing species to support various animals that can depend on this area, whether they were endemic or transient in nature. Sea level rise projection was basically identified here at 8.8 feet. Your higher projection obviously would be at 22, which was up in this area. So in general, the mitigation site would be able to withstand any surge and any projected sea level rise up to the year 2100. And the diversity of habitat is presented here in the cross section. This is an image of what some of the oyster reefs and reef balls would look like, how they're interplaced and staged. They are also put in a specific orientation to not restrict certain breeding activities. Just like the Delaware side on New Jersey, the Raritan does have horseshoe crabs that also utilize certain shorelines. Obviously, populations aren't as great as certain areas of the state, but the intention of projects like this are to improve habitat resources for those types of species. So obviously we know that beaches naturally erode and rebuild over time. The process of erosion has accelerated in recent years, very likely an impact of increased storm frequency, climate change, and sea level rise. The establishment of near-shore shell bars or oyster whelk shell reefs reduce erosion and help naturally trap sand and raise beach elevation over time. One unique fact is one adult oyster filters and cleans up to 50 gallons of water per day. So obviously, these oyster reefs, as they propagate and expand with the baseline support that we put in, the intention is for there be localized water quality improvement as well, aside from providing benthic habitat and foraging and shelter resources. And in general, when used correctly, they protect the shoreline. Here on the right, you can see several artificial reefs that are established throughout the state. Some of these also on the Delaware side, you can see in this image, are several projects like this that the littoral societies and other entities have put these oyster reefs in place and have worked very well. So to kind of summarize how this was all integrated into a sustainable design, here's a plan view of the overall design and its various components. As I described, the focus was to do something that was resistant, and resilient to sea level rise to the year 2100. Use the limited space to truly diversify habitat to various species and provide shelter, foraging, and nesting resources for all those species that would be benefiting from this specific area. And at the same time, provide a natural measure of protection for the adjacent inland improvements, as well as the bridge itself. So here we have the, so my cursor, we have the reef balls again. We have the integrated oyster reefs or whelk shell reefs. We have emergent vegetation, basically your low marsh, and then you have your high marsh vegetation in these specific areas. And these pockets eventually would fill in and at the same time allow passage for species, whether it be fish or crabs. And that's topographically, everything's vegetated and anchored through the various species that we select and stabilized against future storm surge. There is also various man-made structures for tree swallow nest boxes that obviously would improve localized habitat and activities for that species. There's also an osprey nest that we are proposing on the mitigation site as well. Before the project was initiated, the adjacent property did seem to have some raptor activity, and that was actively remediated. So putting something in place like this will definitely, we do foresee that it'll provide a habitat value. But in short, this is what the project consists of and the considerations we took to obviously have an immediate impact and a long-term project that could withstand surge and obviously provide long-term benefit to local wildlife.